Today we're going to explore the idea of finding the gradient function of a curve. We already know how to find the gradient of a straight line because it's simply the coefficient of x, or it's simply how far in the y direction the line goes with one movement in the x. So for a line such as y equals 4x plus 1, I could work out the gradient by moving across one distance in the x, and that would correspond to 4 distance in the y, so that would be a gradient of 4. However, what I want to explore today is how can I do that for a line, so let's say a quarter of x squared. What would the gradient of this curve be? And hopefully we could see that the gradient would change depending on where we are, because on this left hand side it would be negative, and on the right hand side it would be positive. One way to think about this is if I plot a point on here, so like A and f of A, that would be a point, and this can move along the line, and I could explore the tangent of A, and we can see that the tangent is changing depending on where A is. So unlike our straight line, the tangent or the gradient function of this curve will constantly be changing. So what I want to think about is how can I work out what that is? So I know I'm looking at the tangent function and I want the tangent of A. So I'm just going to plot that back again, but this time I'm not going to move point A. I'm just going to leave it where it is. And I'm going to introduce a second point, because in order to get the gradient of a line, I need to work out the gradient between the 2 points. And obviously with A and the tangent, I don't have a second point, so I couldn't currently work out the gradient of that line. So I'm just going to introduce another point, and I'm going to call that B and f of B. And this will create a slider as well that I can move. And let's say that B starts off up here somewhere. And if I draw a line through those points, so through both point A and B, that will give us a rough approximation for what the gradient is. So I'm just going to change, I'm just going to change my actual colour of the line just to make it a bit more obvious. So it's the red line is what I'm looking at. And I want to think about what value of B is going to make this red line a better guess to the black line. So as I reduce, or as I increase my value of B, let's look at that first, we can see that my red line is getting further away from my tangent. And as I decrease my value of B, we can see that my red line is getting a better and better and better approximation for the tangent, until we get to a point where we are so close to A that my red line is almost on top of my black line until they are eventually equal. And then again, as we get further and further away, we can see that my tangent line gets further away. Or sorry, my gradient of the line gets further away from the tangent. So I want to explore what's actually happening here, but the main takeaway from this is that as B gets closer to A, my gradient of the line between them gets closer to the gradient of the tangent. Okay, so I'm just going to draw out the system we just had. So we had our axes here, and we had some curve. Let's just call it f of x. And I had a point, which I didn't mind where it was, so let's just call it our x coordinate. And let's say we were looking at a graph of x squared. I know we weren't, but let's say we were. My corresponding y coordinate would just be my function of x, whatever it was. It wouldn't matter in this case that it was x squared. And what I introduced was the idea of this second point, which was larger than x. And again, the corresponding y value of that second point was just what would happen when I substitute that into a function. Okay, now we need to think about what is going to happen to make this a better approximation. So at the moment, if I found the gradient, it would be finding the gradient of this chord here joining the 2 points. Hopefully we can see as this chord gets closer and closer to the value of x, we get a closer and closer approximation to what the gradient would be, which would be something similar to this. So what we're doing is I'm going to have to introduce a limit. So what I want my h value to do is to get closer and closer to 0. So the way I represent this in maths is I say the limit as h approaches 0. So this is the limit of h. If you could make a note of that, that would be great. Obviously, h can't equal 0, because if that was the case, we wouldn't have 2 points. They would just both be x, and therefore we couldn't find the gradient of the line. So, if I want to find the gradient function of the curve, I would first of all want to find the derivative of x, well, our function of x. So to do this, I'm looking at the limit as h approaches 0, but I'm looking at that with respect to, well, how do I find the gradient of a straight line? Now, the gradient of a straight line is the difference in the y values over the difference in our x values. So our y values are f of x plus h, take away our f of x, all divided by, apologies about that, all divided by our x plus h, subtract our x. I can clean up this bottom, the denominator of a fraction, by writing our gradient function is equal to the limit as h approaches 0. My numerator can stay the same as f of x plus h, take away the f of x. However, my x values are going to cancel out at the bottom and I'm left with a h. And again, this reconsolidates the idea that if h was equal to 0, we would be in big trouble here because we can't divide by 0. So, what can we do from here? We can think about what happens for our specific case if I had a graph of x squared. So if I had a graph of x squared, what I can do is I can change these f of x over here, because I could now work them out if I'm using x squared. My y coordinate of x would be x squared, and my y coordinate of x plus h would be x plus h squared. So looking at this specific example, I could have the gradient function is equal to the limit as h approaches 0 for, well, my f of x plus h is x plus h squared, take away my x squared over h. And doing a little bit of expanding here, as h approaches 0, I'm going to get the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, or subtract x squared, sorry, divided by h. And what do we notice about this? Well, what we should see is that I'm going to have an x squared here and a subtract x squared towards the end, so they can cancel each other out. And I also have a h in the denominator, and now I have a h in each of the terms above. So this h is going to cancel with a h here, and also that little h squared. So rewriting this, it's the limit as h approaches 0 of 2x plus h. This is where it's important that we think about what does it mean to have a limit. So this idea is as h gets closer and closer to 0. So if I had a function, so 2x plus h, and I want to know what happens when h gets closer and closer to 0, well, 2x at a value really, really close to 0, so let's say it's approaching 0, would just leave me with 2x. Because once h gets infinitesimally small, there's no real reason to add it on. So therefore that leaves me with the idea that my gradient of x squared is 2x. Now what I'm going to do is I'm just going to try and verify this by looking at Geogebra. So I'm just going to cancel everything I've done so far. I'm just going to plot my graph of y equals x squared. And then I'm also going to look at a point on there, so a and f of a. And then by plotting the tangent function of this point, I want us to pay close attention to what the gradient is with our x-coordinate. So at the moment our x-coordinate is 1 and my gradient is 2. By thinking about this, I should always have my gradient being twice that of my x-coordinate. So if I increase it to, let's say, 4, I would be assuming that my gradient would be equal to 8. Just going to use it on here, and lo and behold it is. If I want it to be negative 2, my gradient should be negative 4, which it is, and likewise with negative 5, it should be negative 10. The process we've just done is called differentiation by first principles, and the main formula that we look at is this formula here, where it says the derivative of x is equal to the limit as h approaches 0 for the function of x plus h subtract f of x, all divided by h. So if you could make a note of that, please, somewhere in your book or on a piece of paper and bring it with you to next lesson, that'll be much appreciated. Thank you very much for watching.